On the 4th of July, in the year 1054, astronomers of the Chinese imperial court recorded something that shouldn't have been possible. A new star blazing in the constellation we now call Taurus. Not a comet, not a planet, a star that had simply appeared. It burned so fiercely that for 23 days you could see it in broad daylight. They called it a guest star. It lingered in the night sky for nearly 2 years, and then it faded, and the sky closed over it, and the world moved on. What those astronomers could never have known is this. The star they watched die had already been dead for 6,500 years. Its light just took that long to cross the gulf between us. And the event that killed it, the actual moment of death, took less than 1 second. Tonight, we're going to live inside that second, because buried in it is the answer to a question you've probably never thought to ask. Why does your blood carry iron? Every star in the sky is a war that hasn't finished yet. On one side, gravity, patient and relentless, trying to crush 1,000,000 Earths worth of matter into a single point. On the other, nuclear fusion, the engine at the core hurling out enough light and pressure to hold the collapse at bay. Our own sun pays for this ceasefire by burning 600 million tons of hydrogen every single second. It has kept that up without a single missed payment for 4.5 billion years. And because it's a modest, careful star, it can afford another 5 billion. But the guest star of 1054 was nothing like our sun. It weighed about 10 times more, and for a star, being heavy is a death sentence. The extra weight squeezes the core hotter, the fire burns faster, and the fuel that should last 10 billion years is gone in 20 million. A sun like that doesn't get to fade away peacefully. It's forced to improvise, and what it does next is one of the most desperate acts in the universe. When the hydrogen runs low, the center contracts and ignites its own ashes. Helium becomes the new fuel. When the helium runs out, the ashes of that fire ignite. Carbon, then neon, then oxygen, then silicon. It's climbing down a ladder, and every rung is hotter and every rung is shorter. Hydrogen burned for millions of years, helium for hundreds of thousands. Carbon is gone in a few centuries. Neon lasts about a year. Oxygen, a matter of months. And silicon, the final rung, burns for a single day. Picture the giant in that last day, an onion the size of a solar system, every layer burning a different element, and at the center, the furnace fusing silicon into one substance it can't use: iron. Iron is where the ladder ends. Every element before it releases energy when it fuses. Iron doesn't. Iron takes. Fusing iron drains the fire instead of feeding it, which means the core is now filling, gram by gram. With dead weight, the engine can't burn. If you were standing on a planet orbiting that star, nothing would look wrong. The light on your face would feel steady and warm. Sunsets would look the way they always had. The surface of a dying giant carries no warning at all, because the disaster is sealed thousands of kilometers below, in the dark. Down there, an iron ball the size of the Earth is growing heavier by the hour, creeping toward a very precise threshold, about 1.5 times the mass of our sun. Astronomers call it the Chandrasekhar limit. The star experiences it as the last gram it can carry. Now, count to 1. In the time that took you, that iron heart gives up. The pressure holding it open fails, and a ball the size of planet Earth collapses to the size of a city, Boston or Frankfurt, in a quarter of a heartbeat. The infalling matter reaches 70,000 kilometers per second. That's a quarter of the speed of light, achieved from a standing start, in milliseconds. The atoms themselves don't survive. Electrons are rammed into protons. The familiar architecture of matter, the airy, empty atom, is abolished, and what remains is a solid mass of neutrons packed shoulder to shoulder, as dense as an atomic nucleus. A single teaspoon of it outweighs a mountain range. And here, at the very bottom, matter plays its final card. Neutrons can't be pushed into each other. It's one of the deepest rules in physics. The collapse slams into that rule like a train into a cliff face, and the whole avalanche of infalling stellar material bounces. A shockwave erupts outward into the falling layers. The energy released in that single second is so far beyond ordinary numbers that it needs its own comparison. More energy than our sun will produce in its entire 10 billion year lifetime, released at once, in a space the size of a city, but almost none of it comes out as light. 99% of the explosion leaves as neutrinos, ghost particles so reluctant to touch matter that they stream through the entire dying giant as if it were glass. To feel what that means, 100 trillion neutrinos from our own quiet sun will pass through your body in the next second. You've never noticed a single one. Now scale that source up by the brightness of 100 billion suns, and you have the flash of a collapsing core. The light, meanwhile, is trapped. It has to fight its way out through the exploding layers, and that takes hours, which leads to one of the strangest facts in modern astronomy. In February of 1987, a star collapsed in a neighboring galaxy. Deep underground, in a mine in Japan and a salt cavern under Lake Erie, detectors built for entirely different purposes suddenly counted 24 neutrino strikes in 13 seconds. 3 hours later, the sky above the southern hemisphere lit up with the first naked-eye supernova in 4 centuries. The dying star's last breath arrived before its own light. We heard the collapse itself. And since May of 2023, we've been listening for something even earlier. Japan's 2 great detectors, Super Kamiokande and Comland, now run a joint alarm that watches for a different signal: the neutrinos of the final fuel. In the last days before collapse, as the dying center burns silicon, it hums louder and louder in neutrinos. And for a close star, that hum is loud enough to hear. Not hours after the death, hours before it. Keep that thought. We'll need it at the end. Because this is where the violence turns into you. That shockwave tearing outward through the doomed giant is briefly the most creative place in the universe. In seconds, it forges elements it could never make in life, and hurls them, along with everything it spent 20 million years building, out into the galaxy at 1/10 of the speed of light. The iron atoms in your blood, carrying oxygen to your brain as you watch this, forged in a collapsing core. The calcium in your teeth, the oxygen you're breathing right now. None of it existed at the beginning of the universe. The Big Bang made hydrogen, helium, and almost nothing else. Everything heavier had to be cooked inside a star and then scattered by its death. You're not made of stardust in the gentle, poetic sense. You're made of shrapnel. And the very heaviest elements, gold, platinum, and uranium, are mostly not even made here. They need something rarer. 2 of those city-sized neutron cores, the corpses of past supernovae, spiraling into each other and colliding. A single such collision, observed in 2017, appears to have minted more gold than exists in the entire Earth. Every ring on every hand on this planet is debris from dead stars colliding. And what does a collapse leave behind? If the collapsing core is light enough, the bounce holds, and what survives is a neutron star, a sphere 25 kilometers across, spinning up to hundreds of times per second, with a magnetic field 1 trillion times stronger than Earth's. The most extreme solid object that can exist. Stranger still, we knew about these corpses before we ever found one. In 1934, 2 astronomers, Walter Baade and Fritz Zwicky, proposed that a collapsing star could crush itself into pure neutrons, and coined a word for the explosion that would make one: supernova. The neutron itself had been discovered just 2 years earlier, Colleagues shrugged. Zwicky, never diplomat, called his doubters spherical bastards. Bastards, he explained, whichever way you looked at them. The universe took his side in 1967 when a graduate student named Jocelyn Bell caught a radio signal pulsing from deep space like clockwork. The dismissed corpses of Bod and Zwicky, real, spinning, and screaming across the radio sky. But if the core is too heavy, more than about 3 suns, then even the neutron wall fails. The collapse continues past every rule matter has. No bounce, no forge, no second act. The star doesn't become a new kind of object. The star becomes a place, a region of space that light enters and never leaves. If all of this sounds like ancient history, it isn't. On the 19th of May, 2023, a retired engineer in the mountains of Japan pointed his backyard telescope at the Pinwheel Galaxy and caught a brand new point of light. His name is Koichi Itagaki. He hunts supernovae as a hobby, and this was roughly his 170th catch, the closest one to Earth in a decade. Within days, astronomers were digging through old Hubble images of that exact spot, and there it was, the victim. A red supergiant, 17 times the mass of our Sun, shrouded in its own shed dust, photographed alive again and again, over more than 20 years, by cameras that had no idea they were taking portraits of the condemned. The astronomers of 1054 saw a guest star and could only wonder. We can now pull out the family album of the deceased. Which brings us, finally, to the one hanging over our head tonight. Go outside tonight and find Orion. The hunter's left shoulder is a star called Betelgeuse. You can see with your naked eye that it's orange. It sits about 600 light-years away. It's 700 times wider than our Sun, and it's dying. The hydrogen years are long behind it. It is somewhere on the lower rungs of the ladder, shedding clouds of its own substance into space. And in 2025, this old giant gave us a genuine surprise. Astronomers finally confirmed something hiding in plain sight. Betelgeuse isn't alone. A small companion star, nicknamed Sawarha, her bracelet, was caught on camera for the first time, orbiting so close that it plows through the outer layers of Betelgeuse's atmosphere every 6 years. It solved a mystery that had puzzled observers for a century: the slow 6-year rhythm in Betelgeuse's brightness. That rhythm is the wake of a hidden star, swimming through a dying one. Enjoy her while she lasts. The orbit is decaying, and one day Betelgeuse will simply swallow its own companion whole. Then sometime in the next 600,000 years, which in stellar terms is next week, the iron heart of Betelgeuse will touch that limit we spoke of and count to 1. When the light of that second reaches Earth, Betelgeuse will outshine the moon. For weeks, you'll see it in daylight, and after sunset, it will cast shadows. Then, over months, it will fade, and Orion will have lost his shoulder, permanently, for every human generation that follows. At that distance, it's far too remote to harm us. We just get the front row seat to the most violent single second nature can produce. And this is the thought to take to bed. The light arriving from Betelgeuse tonight left it around the time of the plague years of the Middle Ages. Anything that's happened to that star since, anything at all, is still in transit. If the collapse has already come, then a wall of neutrinos is racing toward Earth just ahead of the fire. And thanks to those silicon-burning hums, the detectors under the mountains of Japan would raise the alarm hours before the sky changes. The astronomers of 1054 got no warning at all, just a guest arriving unannounced in broad daylight. We'll hear ours knocking.